Okay, so it's my pleasure to welcome all of you to this HoloTube Jr event that we take place all this week. And so the idea is to let all our participants to talk about their work and to present their ongoing or published work. So the rules are as always, so they stay for the same as in all the other meetings. So you are welcome to ask questions to the speaker. And if not very urgent, please just raise your hand or write it in the chat or wait for a pause. And apart from that, I'm very happy to introduce our first speaker of the morning session. So it's Ioannis Matthaiakakis from University of Würzburg, and he will tell us about his recent work about turbulent hydrodynamics in strongly correlated Kagome materials. Please, Ioannis.
Okay. Thank you for the introduction, and let me from my side thank the organizers of this webinar series and welcome all to this event. So today, as Matteo said, I will be talking about some recent work with my collaborators that appear in Nature Communications on turbulent hydrodynamics in strongly correlated Kagome metals. But before we get into that, I want first to give you some motivation and an overview of this talk. So as you all know, when we increase the coupling strength of the system from the perturbative to the non-perturbative regime, we can expect to see new and interesting transport phenomena. Examples of these phenomena are high TC superconductivity, quantum critical phases in metals, and of course, the quark gluon plasma at LHC. As well, also, when we have a system that we know exhibits a strong coupling, we can use it as inspiration for developing new AD-CFT models. Or on the other hand, we can use existing AD-CFT models to predict new transport properties of a strongly coupled material. This work takes the second route, and I will use AD-CFT to predict new phenomena for a strongly coupled material. To be more precise, I'm going to focus on the transport phenomena affected by the ratio of shear viscosity to entropy density, eta over S. In case you don't know, the shear viscosity eta is given by the imaginary part of the off-diagonal components of the energy momentum tensor, the two-point function. And this formula tells us that the physical meaning of the shear viscosity is that when you introduce, this two-point function tells us how easily a shear stress propagates from one point in the system to another point in the system. So for example, if you have a two-dimensional fluid moving in a wire with one of its boundary plates being stationary and the other boundary plate moving with a velocity u, the shear viscosity tells us how easily it is for the upper boundary to drag along the rest of the fluid. Now, the shear viscosity has a well-known coupling dependence in the perturbative and in the infinite coupling regime. In the perturbative regime, we know that eta over S scales like 1 over alpha squared, where alpha is the effective fine structure constant in the system dictating the electron-electron interactions in the fluid. On the other hand, in the non-perturbative regime, the holographic regime, we know that rotationally invariant relativistic fluids satisfy the so-called KSS bound, where eta over S takes its minimal value 1 over 4 pi, h bar kb. Now, the exact value eta over S takes does affect the transport properties of a fluid in non-trivial ways, such that, for example, if you have a metal with a value of eta over S closer to the KSS bound, then it will be a better conductor of electricity than a perturbative material, since it will exhibit a smaller resistivity and decreased heating when you pass a current through it. Also, eta over S affects what is called the Reynolds number of the system. The Reynolds number is a phenomenological parameter whose value tells you whether you can expect the flow in the wire to be laminar or turbulent. For the case of 2 plus one-dimensional fluids, when the Reynolds number is much smaller than 1,000, you can expect the flow to be completely laminar, which means that the velocity profile drawn here with these arrows is a completely regular function of space-time. On the other hand, when you increase the Reynolds number over 1000, you can expect fully developed turbulent behavior, which means that you can expect the forming of vortices that propagate in the system, and the velocity profile starts showing discontinuities because of the strong fluctuations in the particle movement in the fluid. More importantly, the Reynolds number depends on eta over s and depends as the inverse of eta over s. This means that the smaller the value of eta over s, i.e. the larger the coupling of the system, the larger the Reynolds number becomes and the easier it is for turbulence to set in. With that in mind, this is the punchline of my talk. So I'm going to propose a strongly coupled Dirac material, scandium heterobentonite, that exhibits a fine structure constant of with a value of 3, well into the non-perturbative regime. Then I'm going to give a holographic model that I will argue is good enough to describe some of its properties. I'm going to argue that a strongly coupled material exhibits a more robust hydrodynamic regime with a small caveat I will explain later. Then I will estimate eta over s for scandium heterobentonite and use that estimate to show that it gives us access to the fully turbulent regime by estimating the Reynolds number. Now, the way I'm going to do all that is through this outline. First, I'm going to discuss a little bit about electron hydrodynamics. Then I'm going to describe Kagome materials and the specific proposal for a strongly coupled one. After that, I'm going to use AD-CFT to give an estimate for eta over s and use it to estimate the Reynolds number. And after that, I will give my conclusions and an outlook of this work. As Matteo said, feel free to stop me at any time for questions. By the way, I don't see the chat, so please speak up if you have any questions. Okay, so we start off with electron hydrodynamics. So hydrodynamics in general can be defined very loosely as the long wavelength, small frequency description of thermalized matter. And by long wavelength, a small frequency, I mean that we describe the system in length and time scales that are far larger than the typical time scales of the system, such as the inverse eigenfrequencies of the particles moving around and any relaxation time. Of course, that means that when we describe the system in terms of hydrodynamics, that we lose any direct access to the microscopic degrees of freedom. However, these microscopic degrees of freedom do leave their imprint on hydrodynamics, and more precisely, they specify when hydrodynamics is applicable. To be more precise, for electron hydrodynamics to set in, well, this condition must be satisfied, which tells us that the electron-electron scattering length must be far smaller than any length scale in the system, such as the electron impurity scattering length, the electron phonon scattering length, and any geometric scale in the system, such as the width of a wire where the fluid is moving in. Now, we know that from perturbation theory that the electron-electron scattering length depends scales like 1 over alpha squared with the effective coupling of the system, and the effective coupling of the system is the usual fine structure constant, you know, from KD. But since we're in a Dirac material, we're interested in Dirac materials, the speed of light is replaced by the Fermi velocity of the system, and the permittivity of the vacuum is corrected by the electric permittivity of the material. So you see from this formula here that the smaller the Fermi velocity of the system is and the electric permittivity, the larger the coupling becomes. And the larger the coupling becomes, the smaller LE becomes, which means that for a strongly coupled material, it's far easier to satisfy this inequality and have electron hydrodynamics. However, this is where the small caveat enters that I showed you earlier. This is not the only condition for electron hydrodynamics to be valid. You must also make sure that the energy you're probing the system in is smaller than the energy where non-hydrodynamic modes start to appear. And recently, Matteo Bacchioli has used experimental data for electronic fluids to estimate that energy scale where non-hydrodynamic modes appears, and has shown that the stronger the coupling becomes, the smaller the energy scale for the non-hydrodynamic modes to appear is. Also, Andrei Starinets, during his last HoloTube seminar, has also indicated that this is probably true for holographic fluids as well. So this means that for the rest of the talk, if when I say that stronger coupling enhances hydrodynamic behavior, I will mean that it makes it easier to satisfy this condition as long as you are probing the system at energies smaller than the energy where non-hydrodynamic modes appears. Okay, and with that caveat out of the way, this is the prototypical relativistic electronic fluid of the past decade or so, graphene, with its hexagonal lattice and the relativistic spectrum shown here, with a Fermi velocity given by the speed of light over 300. And the interesting thing about graphene is that one of the interesting things about graphene is that it gives you access to quantum critical behavior when you pin the Fermi level on the Dirac point and you have a vanishing global charge for the system. However, despite all the advantages of graphene as an electronic fluid, it still can only be made pre-turbulent and can achieve a Reynolds number of order 100. This value of the Reynolds number can be achieved by a simple method. You take a graphene channel shown here, you put a large obstacle drawn in black here, and you let the flow go around it. As you can see, some parts of the flow here drawn have a larger velocity indicated by the color, which says that some vortices have started forming in the system. But again, this is still not enough to have a fully developed turbulent behavior. Okay, so this concludes what I wanted to say about electron hydrodynamics. And unless you have any questions, I will proceed with Kagome materials and my proposal for scanning Herbert Smithite. Okay, let me proceed. So Kagome materials are based on Kagome lattices, and Kagome lattices are based on this Japanese basket weaving pattern with its trihexagonal symmetry, which carries over to the lattice. So due to this trihexagonal symmetry, a Kagome lattice also has a point in the Brillouin zone where it exhibits a relativistic spectrum. And it also has, and also Kagome lattices are defined such as there are 3 sides per unit cell. This means that Kagome lattices are inherently robust against magnetic ordering effects, which, for example, you can see that if you try to bring a Kagome lattice into an antiferromagnetic phase by putting anti-aligned spins in its lattice side, you find that this is impossible. And to produce a Kagome material out of this Kagome lattice, what you do is you take some atom and you place them on these colorful sites. And this is exactly what we did to create scandium substituted Herbert sites. So we took copper atoms indicated by the blue spheres here, and we used oxygen, hydrogen, and more importantly, scandium as the binding agent between these copper atoms. Now, the important thing here is that when you use scandium to bind the copper atoms together, you allow the copper atoms to hybridize in terms of d orbitals, which makes them more strongly correlated. This means that the electrons will want to spend more time around the copper atoms than to propagate in the rest of the lattice. As a consequence, the spectrum of Herbert Smithite, which you can see here drawn as a function of the momentum in the Brillouin zone, will still exhibit a Dirac point due to the hexagonal symmetry, but will have a spectrum that is more flatter than, let's say, graphene with a very small Fermi velocity. Another important feature of scandium substituted Herbert Smithite is that this substitution brings the Fermi level of the system directly on top of the Dirac point, which means that you still have access to quantum critical charge neutral physics, such as those found in graphene. Finally, using scandium puts us away from what is called half filling, which again means that scandium herbate is robust against long-range magnetic ordering, which would break the hydrodynamic behavior of the system. But besides all this fancy stuff, the most important fact about scandium herbate for us is its coupling strength. So recall that the effective fine structure constant in electronic system is given by this formula with the Fermi velocity and the electric permittivity. And if you plug in the values given for scandium herbate here, you will find that it exhibits a coupling strength of 2.9, well into the non-perturbable regime. For comparison, we have graphene, encapsulated graphene in hexagonal boron nitride, with a coupling constant of 0.9. This means that while you can hope that perturbation theory might give you something resembling reality from graphene, this hope is dead when you try to describe scandium herbate. Okay, and this concludes my proposal. Are there any questions before I move on?
Can I ask a question?
Yeah, of course.
So can people actually synthesize this material?
Scandium herbate itself has been very difficult to synthesize so far. It's not impossible, but because you have to substitute scandium in the whole system, it's tricky to do stoichiometrically. But in principle, it's possible. Furthermore, this material might be the one I'm proposing here, but there is a larger class of Kagome materials that are easier to synthesize and have a similar coupling strength. Okay.
But these are not the materials that you will discuss later on in the talk.
They have the similar they're basically the same, but have a different coupling strength. So the properties I'm going to be discussing are the same for these materials.
Okay.
Okay. Any other questions? Okay. So I'm going to move on to ADS-CFT. Now, as I said in the beginning, I want to find an estimate for eta of RS in scandium herbate, and I cannot do that using perturbation theory. So I'm going to resort to holography. And what I want to do is to calculate this two-point function and calculate eta. So the typical calculations in ADS-CFT are using the Einstein-Hilbert action are at an infinite coupling strength. However, we are no longer at an infinite coupling strength, we are at the very finite coupling strength of 3. So I need to introduce coupling corrections into that Einstein-Hilbert action. To do that, I would just introduce higher derivative corrections of the fields in the gravitational action. Also, you would expect that since we're talking about an electronic system, the Maxwell terms would be important in the gravitational action. But since I'm interested in physics around charge neutrality, they play no role. This means that the effective gravitational action of the system is just a function of the metric and its derivatives. To be more precise, this is the effective action I'm going to use. So we are in 4 bulk dimensions. We have the usual Einstein-Hilbert term, and these are the higher order corrections, which are schematically given here. So R squared contains all the contractions of the of 2 Riemann tensors, 3 Riemann tensors, and 4 ones. C1, C2, and C3 here are numbers of order 1, and alpha prime is the string length squared, which is the natural length scale that appears if you try to write down a top-down construction of this gravitational action. So I'm going to use these higher derivative corrections to see what happens to eta of RS. Now, let's take these terms one by one. The first quadratic term can be brought to the form of a Gauss-Bonnet form, of the Gauss-Bonnet term, which is topological in 4 dimensions, so it does not affect the dynamics of the system, and as a consequence, it does not affect the value of eta over S. So I can set C1 to 0 without loss of generality. Next, we have the cubic terms, and these have been shown to be inconsistent with a top-down string theory construction of gravitational actions, since they don't respect supersymmetry. Also, if you don't care about supersymmetry, these terms have been shown by Caramagno, Edelstein, Maldacena, and Tsiboedov to break the causality of the boundary S matrix at tree level. So you can you must set C2 to 0 to respect causality as well. This means that the only relevant term that remains is the quartic term in the curvature, and this is the simplified gravitational action. And we will use that to calculate eta over S. And the result is this. So we have the usual 1 over 4 pi result from the Einstein-Hilbert term. And we have the higher derivative correction coming from the quartic curvature corrections, which scale like alpha to the -3/2, and C is an order 1 coefficient that depends on all the prefactors that appear in the quartic corrections. So now, to give an exact value for scandium Hilbert-Smithite, I must know the exact top-down string theory construction of the system. But since I want to describe a larger class of materials like Hilbert-Smithite, as I mentioned earlier, what I'm going to do instead is to parameterize. I will take this as an unknown number and parameterize the value of eta over S as a function of that. Doing this, we end up with this graph where on the vertical axis we have eta over S normalized with respect to the KSS bound, and on the horizontal axis we have the coupling strength. The black curve here is the perturbation theory result, which, as you can see, fades away when you try to take the coupling close to 1, indicating the breakdown of perturbation theory. Also, the red dashed line is the KSS bound. Finally, the blue band you see here is the band generated by this formula over here when you vary C not by an order 1 number, but instead with four orders of magnitude. To justify why we varied C over these 4 orders, note that if the theory in question was n equals 4 mils, this range for C is equivalent to taking the rank of the case group from 2 to 1000. And for reference, ADS QCD is uses an n equals 3 here. So what we see from this graph, we see that for scandium Hilbert-Smithite with a coupling strength of about 3, that the value of eta over S scales, it takes very narrow values from close to the KSS bound up to 2 or 3 times the KSS bound. We take this to mean that holography can be used to give a good estimate for the properties of scandium Hilbert-Smithite and all of its properties, and eta over S in particular. On the other hand, you can compare this with the holographic estimate for graphene, where the value of eta over S scales from 2 to about 8, which seems that holography is not such a good fit here. Fun fact though, the experimental result for eta over S for graphene is about 4 through 8, which means that still holography is a far better fit than the perturbation theory result, at least for eta over S. Now, having these estimates, I can go back to my initial point of the talk and see what happens to the Reynolds number. So if you plug in all these numbers for the eta over S Fermi velocities for scandium Hilbert-Smithite, you will find that its Reynolds number is enhanced by 2 orders of magnitude compared to graphene, which means that it has a Reynolds number of order 1000 to 10,000. And as I mentioned at the beginning, an order 1000 Reynolds number is good enough to have a fully developed turbulent flow in your electronic system. And with that, these are my conclusions. and the outlook. So as I mentioned several times, I propose a Dirac metal, scandium herpesmethite, that exhibits a fine structure constant of about 3, which makes it a non-perturbative material. I argued that it's well suited to a holographic description of its physics. I also mentioned that a stronger coupling enables the transition to the hydrodynamic regime with the small caveat I mentioned about the non-hydrodynamic modes. And I showed you that scandium herpesmethite allows us to achieve a turbulent flow for the first time in an electronic system. Now, for outlook, there are 2 simple questions you can ask. You can combine 2 and 4 and ask whether holography can give you a fully consistent description of turbulence. And on that question, there has been some early work by Adam Chesler and you on holographic turbulence, which calculated the power spectra of some modes in a black hole background. And for more recent work, you can, on holographic turbulence, you can check out the HoloTube seminar tomorrow by Christiana Pantelidou on large number of dimensions holographic turbulence. And you can stick around for, if you're interested in holographic superfluids, you should stick around for a talk by Paul Wittmer up next. Another interesting outlook question is if this material is the only one of its kind. And this answer has been answered in the negative recently by several of my collaborators on this project, Ronnie Tomale and Domenico Di Sande, where they have suggested a similar Kagome Dirac material, which looks pretty much like this one, but which exhibits a fine structure constant instead of 3, 13. So an order of magnitude larger. And with that, I want to thank you for your attention and feel free to ask any questions.
Okay, thanks a lot, Ioannis. So questions, we have plenty of time. Don't be shy.
Hi, may I have one question?
Mm-hmm.
So I'm not sure what do you have in the CFT side, but I guess what you have is Dirac theory plus Coulomb interaction. Am I correct?
Yeah, exactly.
Okay, so then there was a conjecture that once we tune the interaction strength stronger and stronger, and at some point there is a phase transition to insulating phase.
Mm-hmm.
I'm not sure, is it possible to investigate that scenario in your calculation?
Okay, I've heard about this phase transition. The point is that I am not sure it's a physical one. So if we're talking about the same phase transition. So this phase transition for graphene has been estimated to appear at a coupling strength of around 0.9 that I have used here. But numerical calculations on the graphene side have shown that this is not the case. There is no insulating phase that appears. So
yeah, but what I mean is that, I mean, there was a paper by Damson, and what he took is Dirac theory plus a Coulomb interaction. And then he proposed that there would be insulating instability, meaning that at some point Dirac cone just open its gap, and then it's become gap full instead of gapless. But the problem is, like you mentioned, that your colleagues like doing something with alpha super high. So yeah, I mean, I was just wondering, is it possible to include that scenario somehow in your calculation?
In principle, yes, but you would have to introduce a dilaton here, because when you open the gap, you might make the spectrum non-relativistic. So you should have some parameter that drives the opening of the gap. So okay. I think the answer is in principle yes.
Okay.
Introduce a dilaton.
Okay. Okay. Yeah. Thank you.
Other questions? No questions?
I have another question.
Good. Go ahead, Bless.
So with graphene, one might try to argue that it is sensible to start from ADS-CFT and add higher derivative corrections or anything like something like that to make the coupling weaker, starting from the ADS-CFT side, because there's this emergent conformal symmetry at the charge neutrality point. Here, can you explain again? Maybe I missed it, but do you expect the same emergent conformal symmetry? Is there also some kind of relativistic fixed point somewhere?
Yeah, so I haven't got the figure here, but if you plot the Fermi surface of scandium Herbert-Smithite, it's quite similar to the one from graphene. So the low energy dynamics are expected to be exactly the same. There hasn't been a direct calculation on that from the condensed matter side, but from what exists so far from the statics, the Fermi velocity of the spectrum, etc., it seems to be that scandium Herbert-Smithite is a typical graphene-like material.
And what about phonons?
Good question. So phonons, I don't have the plot here, but phonons start appearing, the coupling to electrons becomes relevant for temperatures close to 80 kelvins. So if you are just interested in electron hydrodynamics, you should stick to temperatures far smaller than that.
Okay, thank you.
Anything else?
Maybe I can ask a question. You might have said this, but the eta over S that you calculate is in a relativistic theory.
Yep.
And I think Blaise asked about the excitations in this material, scandium Herbert-Smithite. Do you expect that to change, that it's not going to be relativistic? Or how do you address that point?
No, if you stick to energies close, smaller than when the gaps start showing nonlinear behavior, then the system should behave exactly the same as graphene. So it should have a relativistic excitation spectrum.
Yeah, I guess I'm asking the same question as Blaise. Okay, thanks.
Anything else? Nothing? Okay, then if nothing, let's thank Ioannis again for the nice talk.
Thank you.
And let's move forward.